So I'm Gregoire Aufort. I'm a postdoc at the Institut d'Astrophysique de Paris. I don't know why you pronounce Paris like that. I'm working mostly with Clotilde L'Aigle and Henry McCracken. There are a bunch of other people on this project, but the name of the conference is quite long, way too many words. So I only put people who pay me. So I'll talk about STD fitting in a sense, and about star formation history of galaxies. So this slide has accompanied me since I started my PhD, pretty much. Was already on that topic. So the idea is that I have a few different models for the star formation history of a galaxy. So it's parameterizing the quantity of stellar mass at each time step that the galaxy is forming. And I'll observe the SED on the right. I still don't know my right and my left. I'll observe a few photometric points, and the name of the game is to find the SFH corresponding to that SED. I have a bunch of different ways to define an SED. So here are three analytical ones. Unfortunately for me, so first, how do I go from one to the other? You assume you have some nice code, typically Seagull here, Prospector, Bagpipes, any SED modeling code, which will take your star formation history, your stellar population, will compute a first spectrum, will then attenuate it, and at the dust emission, we'll add the nebula emissions, the redshift, everything else. You can infer all those parameters. I think for this, in this specific case, are like 20 parameters. I absolutely don't care about any of them except for the star formation history, so I'll marginalize over everything else. Unfortunately for me, there are a bunch of ways to define an SFH, and even more ways to define a prior over them. And there's this nice quote in the conclusion of a Leger paper in 2019, which is that the size of the posterior is mostly determined only by the prior. The signals to noise doesn't really matter that much for the size of the posterior, which is quite bad when you want to do statistical inference, especially since I have a lot of freedom in choosing my SFH and my priors. So those are so-called non-parametric star formation histories. So you take a bunch of time bins and you say that the SFR in each time bin is random according to a distribution, here directly one. You can have a bunch of those. You choose the number of time bins. You choose whether they are in log scale or linear. And you choose the prior. So here you have two alpha prior over the alpha parameter of the Dirichlet distribution. I have no intuition whatsoever of what's a good prior for star formation history. I think nobody does. And I'm a statistician, so I'm quite bothered by it. Fortunately, we have simulations. So I'm sorry, I'm an outlier for now. I think someone else will use Horizon IGN. I'm not using CAMELS. I don't even feel bad. So most of the heavy lifting on the simulation part has been done by Johan Dubois on Horizon AGN, from which I'll be using a few hundreds of thousands of galaxies at redshift between 0 and 4, down to stellar masses of 10 to the 9. The star formation history is then the product of the hydrodynamical simulation, and the other part of the heavy lifting is getting the galaxy photometry, which has been done by Clotilde L'Aigle. So the big part of the pipeline Lucia was talking about yesterday has already been done. I'm doing the end of maths part, i.e. the inference. Okay, so I can take what Clotilde extracted from the simulation on the left. I have an amount of mass that has been, of stellar mass that has been formed at given time steps in lookback. And I want to infer that given the photometry. So two problems. If I want to infer that directly, I need to infer the time steps and the mass formed. And there are a few thousands of those. It's not a nice problem to sample from. But fortunately, Kartikeya had a great idea in 2019, which is to not look directly at the SFH, but at the cumulative distribution of mass. So you look at the time at which a given mass quantile has been formed, and this is a lot nicer. You can go from one to the other. If you know one, you know exactly the other. But this one is way better behaved for this reason, in that I can fix the mass quantile I always look at. So I can say, OK, I will infer the times at which 5% of the mass has been formed, 10, etc. So now I only have one vector of quantities to estimate. And then when I have those, I will simply interpolate between them to reconstruct the entire cumulative distribution and inverse the operation to recover the SFH. I can choose quite arbitrarily the number of time steps I'm estimating. OK, so if I take, so what I did is I set the number of time steps to 30 because I'll use neural networks. It's low enough to be sampled and big enough to be precise. So here we see the error of the interpolation process and the inversion. So the real one is in blue, and the reconstructed one using only 30 time steps is in orange. And you see that you can have a large variety of SFHs. So these are completely quenched on the third on the right, clearly very active on the left, starting at different points at different redshifts. And now I have a problem on which I can meaningfully perform inference. And to do that, I use SBI. So there was some talk about machine learning as a black box. And I don't really feel it's the case for SBI, because if you write it, what it really does, you assume you have access to target density, which is the joint here of the photometry and SFH. You are learning a density which is minimizing the Kullback-Leibler divergence to that density. And then you'll use your approximation to perform inference instead of the posterior. If I were to do that with a Gaussian mixture, nobody would argue that it's a black box. Simply the distribution is parameterized by a neural network. But I don't really have a problem with that. Ooh. OK, so on one galaxy, on one example, you can, on blue, you have the right one, on orange, the median of the posterior, and the 95% interval, credible interval in pink. So on the left, what you sample directly, and then you invert it and recover samples from your star formation histories. We can check that it works on the simulation. That's the easy part, right? So my estimates are mostly unbiased. There is some small scatter, but it's OK. And my credibility intervals are well calibrated, very slightly conservative at the 50, 68, and 95% level. But I'm very glad with this calibration. OK, this was on simulated data, and we all know doing machine learning on your training set is very easy. We're interested in doing Bayesian inference, and since we are doing SBI, we are assuming that the training set has been sampled by the prior predictive. Otherwise, you're not doing Bayesian inference. And now the question, but it's an old one, it was already asked by Box in 1980, is how do you check that your prior distribution is kind of reasonable for your data? So you observe a galaxy X-ops, and you want to know whether you should have used another model, or if this one is fine enough. The idea is quite simple. You define statistics, so a way to measure in distance in that case, and you check that your observed statistic is not too extreme in the sense of an epsilon, given the prior predictive. What does that mean if you consider the Gaussian case and if you consider the statistic to be the negative log likelihood? You will check that the density of your observed quantity is high enough given the prior predictive distribution. But if you set it like that, well, it's clearly an outlier detection problem. So I have to set a rejection threshold and then say, OK, everything that's outside this region is too extreme, and I'm not satisfied with it. We've had some talks about outlier detection in this case. And we have a lot of different ways to do that. We can define a bunch of statistics, and we have a bunch of different algorithms. In fact, we have way too many. And once again, since I'm Bayesian and I don't like to choose, I'll model average over those. So I'll take a few of them that are different, so some distance-based, some density-based. I'll set a threshold, and I'll have them decide whether an observation is in or out, and then I'll make them do a majority vote and decide this way. OK, now some data. So we'll apply it to the Cosmos 2020 catalog. So I have to thank the Cosmos science team who did the other part of the heavy lifting on the data. I have some cuts on magnitudes on redshift. I'm using 8 colors, so 8 difference in magnitudes. I chose a few algorithms implemented in PyOD, which were usable on this data set. I'm setting an epsilon threshold of 1%, so I'm accepting a lot of things, but I have hundreds of thousands of training points. And interestingly enough, on the observed data, given those cuts, I'm only rejecting 2% of the observed galaxy, which is quite impressive. So either my photometry is really not discriminative of my simulation process, possible, or Horizon AGN simulates very well photometry. I don't know. In total, I have about a little more than 150,000 galaxies. Now I can check what my, so obviously on those galaxies, I don't have the true SFH. Otherwise, I wouldn't be here. But I can check that it behaves like I expect. So if I take an NUV-RG diagram, so the absolute magnitudes have been estimated by Lefar, I'm expecting everything above the red line to be passive galaxies that have been quenched, yes, at some point. And below that, I'm expecting a gradient from left to right, from low mass to high mass. And so I see that the low mass ones are a lot more bursty and seems to be a little younger, and the most massive ones are older and a lot more delayed looking, which is OK. Once again, pretty much the same plot. I can check that the galaxies above the red line are passive in the sense of an SSFR estimated below 10 to the 11. And once again, I'm quite OK. It's passive above and active below. Oh, I rushed the end. So I want to remind you that the input is only the colors. So the mass has been normalized, and there is no explicit redshift input. But as you can see, if I look at different mass bins, I see clearly a difference between the recovered SFHs. And if I look at the time of first formation, or the beginning of the SFH, it does depend on redshift, which is logical. And in particular, it never really extends before the age of the universe, the beginning of the Big Bang. So I'm never estimating SFHs that are older than the universe, which could happen. There's nothing preventing it. I can compare with other estimates in the literature. So Minjun Park published like 16 galaxies. There are 8 for which they fitted spectroscopy and photometry using Prospector, I think, and 2 SFH models in green and pink, as you can see, we clearly see the Leja problem that they use exactly the same data, and the posterior variance is very, very different between the green and the pink one. And my estimate in black is broadly agreeing with it. It's clearly quench galaxies. I seem to be missing a feature that's often detected. It might be because I don't have the spectroscopy. There seems to be a burst sometimes before the quenching that I'm not estimating. But we're not really using the exact same data nor the exact same model. And I'll skip over quite fast over the rest. You can compute a bunch of different statistics on those things on every draw, and then look at the distribution of those. And I'll skip over that. The end note is that everything is behaving pretty much as you'd expect, including when compared either with other simulations or with other observations in terms of the formation time of passing galaxies. Yes, so it's on archive. It's been submitted 2 months ago, but the referee still hasn't refereed. If he's in the room, please do. Thank you.
Any questions for Gregoire? Yeah, in the back there.
Yeah, thank you for your talk. It was really interesting. Just maybe on slide 16. Sorry if I missed it, but the different one back. Yeah. So on the right hand, there's like plots of the lines are different colors. Can you just go over like what the different colors represent?
You have different boxes on the left, so the colors on the right are sampled from the boxes on the left. So I'm checking. I'm checking that they are corresponding. So this red line corresponds to the galaxies that are situated in this box on this diagram, and I'm checking that this should look passive, this should look very young and starbursty, and this should look very. It's not passive. The SSFR is above 10 to the minus 11, but it's still clearly more delayed looking in a way than the very starbursty young galaxies.
Thank you.
Any other questions? Oh, we have a question on Zoom.
Yes, we have a question from Zoom from Rodrigo Flores Freitas, who is asking if you have tested if your model is able to correctly predict star formation histories on other simulations, or how much of the model depends on Horizon AGN specific model.
Yeah, so I know for a fact that the galaxy properties in Horizon AGN are not representative of the galaxy properties of my sample. I have a limit in mass, I have plenty of problems. Well, no simulation is perfect. I'm only checking that the photometry produced by the simulation is kind of similar to the photometry I'm observing. So in that way, I'm checking the only thing I can check, which is the observations, the observables. So that's for the Horizon AGN part. I'd really like to do the same thing on other simulations, but I need someone to do what Clotilde did, which is to extract the SFHs and map them to the corresponding photometry with the same level of noise, etc., etc., etc. So I'd like to do it if it's available. Yeah.
Another one? Oh yeah. Okay, let's go. Another. We have time for one more. Quick question.
Okay, so one more question from Zoom. Karthik Iyer is asking, wonderful work. Do you have an intuition for what implicit prior you have learned from the Horizon AGN training set?
No, and so I can look at the distribution of the times at which mass has been formed. It's 30-dimensional. It doesn't talk to me a lot. So I'd have to choose a statistic to look at. So we defined a few of those, and we haven't explored it. We have to decide on a statistic to look at on those and then compare those. But it's quite unclear what does it mean to compare two star formation histories. You can look at some stochasticity, which is very trendy right now in the SFH space. You can look at, okay, it may be above your SSFR threshold, but very bursty or very quenchy looking. It may be very delayed, very stochastic or not. So I'd have to set a metric to look at first and then to explore it on the simulation.
Well, let's thank Gregoire again. Next, we have John, who's going to tell us about how you're going to make us all obsolete, right?
Not at all. In fact, I'm going to talk about how astronomers can be in the loop for AI systems. And so let me grab my clicker. Yeah, so my name is John Wu, and I'm an assistant astronomer at Space Telescope Science Institute. I also have joint appointments in the Department of Physics and Astronomy and also the Department of Computer Science at Johns Hopkins University. So if you're ever around Baltimore, give me a shout. And I'd like to talk to you about how we can learn about the physics of galaxy evolution using sparse coding methods, something from AI and AI safety. So sort of as a motivation, we know in the traditional lambda CDM paradigm that there is dark matter, which sort of sets the backbone of cosmic structure in the universe. And so under gravity, we have halos basically being formed, virializing out of condensing matter. And if you kind of zoom in within these halos or these subhalos, which are contained within the structure, you can actually see, and if you turn on your baryonic vision, you'd be able to see in these simulations the formation of galaxies as they're accreting gas out of the intergalactic medium and basically condensing that gas into sites of star formation. And that's essentially how galaxies are born and how they continue to grow and evolve. It's through the accretion of matter and the formation of new stars. And this is great because you can, enrich the, interstellar medium and intergalactic medium by, having the stars nucleosynthesize these metals, these heavier elements, and pollute them all over the place. Great. And we know, of course, that there's a lot of things you can do with a sufficiently descriptive halo model. But one thing that we typically neglect is, how to leverage the pixel scale information that's contained within galaxy morphologies. And indeed, even some of these cosmological box simulations have a tough time really zooming in and getting the morphologies exactly right. It's obviously, not an easy thing to do. But we've known for 100 years that, that the physics of how galaxies have built themselves up is connected to their morphologies, right? The Hubble tuning fork diagram is evidence of this, and this sort of connection between galaxy physics and the morphologies is something that is now able to be explored through the advent of machine learning. And the way I like to go about this is to say that we love in the data science era to reduce our galaxies or whatever you like to study into just a few summary statistics, a couple of columns in a table, because it's easier to work that way. And some of our favorite features are just taking a model magnitude or some sort of aperture flux, and then maybe a couple of simple morphological parameters. But of course, what you see here is these are 9 galaxies taken from the DCAM legacy survey. They have the same R-band magnitude and effectively the same G minus R colors. But when you look at their actual morphologies, you probably have a better luck looking on the side ones here, because some of them have low surface brightness features. They look completely different from each other, and the morphological difference really encodes, the exactly information about how they formed and evolved. And we want to be able to get at that information. The way that many of us have now sort of turned to extracting that information is by taking convolutional neural networks and somehow learning that information. And so what I'm showing here is a description of a supervised learning problem. You can do this with self-supervised learning, and you can also do a couple of other methods, zero-shot learning, blah, blah, blah. But the idea is the same, that you have these images, and by leveraging convolutional layers, really sequential matched filtering, essentially matched filtering algorithms at multiple scales, and being able to learn the nonlinear dependencies between those, you can extract some sort of useful features which enable you to make some downstream prediction. And I've built my early career on this, which is just to say that CNNs are able to extract the astrophysical information, which allows us to study how they've grown. And so just as some concepts that we've been able to do is, we were able with Sloan data to extract galaxy morphology in such a way that we could predict the mass metallicity relation. In fact, the spectroscopic metallicities of galaxies just purely from 3-band imaging, enough to reconstruct the mass metallicity relation with no added scatter. Another thing we were able to do is to predict the H1 content in galaxies. So this is looking at Arecibo H1 observations of very low redshift galaxies. But again, leveraging the morphological information, we're able to get the gas to stellar mass ratios and predict that very well. And not only that, but use techniques like GradCam, these kind of pixel level interpretability methods to try to understand where in the image do these CNNs look at in order to make their decisions. And and another sort of really startling discovery to me is work that I did with Josh Peak, where we realized that you can actually distill optical galaxy spectra down into a couple number of parameters, but then you can actually predict those parameters directly from optical imaging. In other words, you can take images and get out spectra with pretty high fidelity. And there's additional work that has been built on top of this. I know some folks here have been able to do other types of this, now called multimodal sort of investigations of galaxies, right? Like you're observing them in different modalities, whether it's through imaging or through their multi-wavelength spectra, or perhaps even through, you could think about how you can connect other modalities such as imaging and time domain and so on. So all this has been, shown to be an enormous success of how deep neural networks can learn the astrophysics of different phenomena. But there kind of remains an interesting interpretability question, which is that, when you talk about these features at the end of the neural network, what is it that they've actually learned? And we like to tell ourselves a story, which is like, oh, maybe they learned some, weird nonlinear combination of how point source-like the galaxy is, or, how strong are its dust lanes, or, do they have tight winding spirals? And we say, okay, good. These are the activations that came out of this trained CNN from an input image. But this is totally wrong, right? And so AI researchers have realized this long ago, because when they want to like put guardrails on what a large language model has learned, it would be great if they could see, yes, this is the feature that corresponds to some sort of toxicity, and we're just going to nullify it. But it doesn't work that way, because in fact the activations that come out at the end of these deep neural networks and language models, which are just deep neural networks, is actually basically a combination of all sorts of different features, where all those features' semantic meanings are also totally distributed across all the features. They've given these goofy names like superposition and what's the other one? Superposition and polysemanticity. Anyway, all that's to say that you basically have the semantic meaning of these features is not one-to-one with the neurons. So neural nets don't learn that way, and yet in the mechanistic interpretability landscape, so this is a subdomain of AI research, people actually have begun making headway into trying to understand what they do learn. And so we can ask ourselves, what do our neural networks learn? And so I'm going to take a detour through a method called sparse autoencoders, or SAEs. And this is a way to tease apart what these features that come out of these encoders, out of these CNNs, and what they might learn. So the point of an autoencoder, of course, is to, given some input X, you push it into usually a lower dimensional latent space Z, and then from that bottleneck layer, you actually then reconstruct the input again, right? You get some prediction X hat, which is as close to the original input as possible. That's the goal of an autoencoder. And so what we are doing is we're taking this CNN-produced feature vector, we can push it through an encoder, and basically just produce a sparse number of latent vectors. And so the number of activations, we only choose the top K of them. So in this case, only 4, right? And we're saying, can we distill and can we consolidate all the information in those inputs in just K sparse latent vectors? And in fact, what we actually do is more than K are actually non-zero in the beginning, but then we throw them out. So we enforce the sparsity constraint during training. And then what you can do then is have a decoder layer and then reconstruct this. And so what you get is a linear projection, basically out of this latent space, to give you some sort of interpretable reconstruction, based on how interpretable these latent vectors are. And this is actually something that we did. This was in fact motivated by work that another team that I led did. This multidisciplinary team did on basically leveraging large language models for astronomy research. And in fact, we're actually going to present some of this at NeurIPS. So I'm flying out on Friday. So if any of you guys are there, go and see some of our talks and posters. But you can actually apply these SAEs directly to LLMs and to language data. You can also do, and what I'll show right now, is you can apply these concepts of SAEs to astronomy data. So what we're going to do actually is a bit of a modification. Just going back, if you look at what a SAE does, it's basically this very simple architecture. It's a single linear layer, usually a ReLU or some sort of nonlinearity, and then you just get the sparse latent vector, and then you learn the decoder. Now, this linear combination of latent vectors is important because this gives you the interpretability between the actual feature vectors and latent space. But this encoder up here is extremely weak. It's very inefficient at representing data. Technically, through the universal function approximation theorem, you can represent anything, all this, modulo, how your sparsity constraint. But we can actually put a much smarter encoder in the loop. And so what that means, what I decided to do is actually say, why not just take the CNN and use it directly as the encoder? What we know to be a very efficient and very capable and expressive way to turn this image into some sort of, distill into some features, and we only keep the top K features. And so what I'm calling this is sparse feature networks. And then from that, we can actually make a linear combination of these to make a prediction. So how does this work? Let's see it in action, where we're actually going to take an input image. What you see here is just an example galaxy, and we're going to try to predict 4 optical line fluxes. These spectral line fluxes are very interesting for diagnosing the excitation or the ionization within galaxies. This is commonly used as part of a PT diagram, which is basically you think about the ionization state of the gas could come from star formation activity within the galaxy. It might come from accretion onto a supermassive black hole, or AGN. And in fact, if you have higher ionization, more of the O3 over H beta and N2 over H alpha, you tend to get into the AGN regime. There's obviously a lot more complexity than just that. And in fact, we'll be able to actually see some of this as we train the neural net. So we try to make these predictions, but we sort of impose this sparsity constraint in the SF net. And so let's take a look now. These are, after we've trained the network and we're looking at the validation set, we can actually see which activations are strongest given one of our 4 features that we've learned here, right? There's only 4 features. And the first one that we see actually corresponds very strongly with low metallicity. Okay, they're all the way sort of on the left side of this plot, and if you've ever tried to put stellar population models into these nebular diagnostic diagrams, you'll find that this indeed is where you expect to find the low metallicity galaxies. And you can see exactly what the way you can, their morphological characteristics on the right there. Onto the second feature, we actually find now sort of older stellar populations and higher metallicities over here on the right. By the way, on the left panel, what you're seeing in the white colors, or like the brightest colors, are the ones with highest activations of that sparse feature. And again, this aligns with our morphological intuitions. But this is all learned directly from the data. Now, if we go to the third parameter, this is very interesting because we actually find something that corresponds with high excitations. These are galaxies that look kind of like Lyman break galaxy analogs, or extreme O3 emitters and things like that. And indeed, they are sort of hugging this dividing line, which sort of determines the frontier of starburst galaxies, basically really extreme star-forming galaxies, but not quite AGN. And in fact, the morphological characteristics are exactly what we expect to see. And then lastly, again, there's only 4. I set k equals 4 here, but I've run a whole sweep of experiments. But this is just illustrative to show that now we're looking at sort of the bottom locus of points here on the star-forming galaxies. These are galaxies with like relatively low excitation. They tend to be kind of diffuse galaxies. But again, this is in alignment exactly with what we expect to see. So this is all work that I've submitted already to AppJ. It's in revision and will probably soon be on the archive. Things are looking good there. But the cool thing about this is that you can actually directly connect this, as I said, via a linear combination of these sort of strengths of activations based on the image properties. You can just take a linear combination of these and get out some sort of physical characteristic, in this case, the ones that we've learned. We've done this with the metallicity, the gas metallicity as well, just directly. You can sort of learn that directly. And you can imagine learning all sorts of interesting galaxy characteristics and directly saying, or asking, how much does some quantity depend on this particular morphological question, characteristic? Like one, just I'm sort of shooting at hip now, but like there's there's one question I've always been interested in, which is do satellite galaxies cause bars or spirals? Like, or what is the relationship between them? With this kind of method, we actually can really start to get at the the connection between those two things. I'm going to be careful and say that it doesn't mean that we can say that we have any sort of causality inferred from this. But what we do allow, just like in these past images, is we allow an astronomer to actually interpret what the morphological characteristics should compare to, and how does that map on to the physical state of the galaxy. So I think this is a promising new way to do, basically, again, astronomer in the loop for these kind of AI or deep learning systems. Let me skip that. Just to get straight to the summary, for a long time, CNNs have learned the galaxy physics, but they're the ones that have been doing all the learning, right? We kind of get left out. And yet, with this SFNet approach, we actually can sort of offer the physical interpretation and allow the CNN to produce the actual interpretable features. And using this kind of way, we can now take linear combinations of image features and derive actual physical properties directly from the data. So please stay tuned for this paper on arXiv. I'm hoping it'll be out in early January or so. And I'm right on time.
Any questions for John? Please.
I have like a million questions. That was very cool. But so the first one, I guess, is so with this top K in your latent, so that almost sounds like principal components. So have you checked to see whether like there's like a rigorous analogy there? Like, is it basically just capturing like the top principal components in your latent?
Yeah. So that's a great question. In fact, this is a comparison against principal components analysis of the features that come out, and that's in the discussion of the paper. What's happening here is this is being trained end-to-end with the sparsity constraint, and that's the main difference, right? If you do a PCA, you typically will learn some sort of representation, and then you just hope that they can be linearly combined in some sort of useful way. And so it turns out that at least with PCA, you end up being able to get some sort of interpretability, but it's not the features are not as well aligned. They're not actually guaranteed to give you some, like they basically don't cleanly separate as nicely here. And so far, all I can say is like that is empirically what we are finding, but it's unclear to me if the theoretical motivations show that PCA should be able to do better than that.
Okay. Yep. I do have one more, but I can wait if there are other questions.
Matt?
Hey, John. In your experiments playing with these different features, were there any features that you didn't expect or like that were particularly weird?
Yeah. I mean, so it's interesting. We were able to find features that just corresponded with like random artifacts. Like there was like one feature that was like SDSS light bleed from the red band, and I was like, yes, I know that thing is annoying. Or like here's like where the green filter is miscalibrated and stuff like that. It's kind of interesting because you can marginalize over these junk features, which is also quite nice. The other thing that will happen, of course, is that occasionally you can get features that are only activated for like just 1 or 2 galaxies out of your sample of like 100,000. And I think that's just something due to noise, and we probably could just optimize those away. But those are unclear because they're only activated for like 1 galaxy. I basically just throw those away. So again, it does require us to be a little more careful and actually think about this. It's not a fully automated system. Thanks for the question.
Shai?
Thanks, very nice. I didn't quite catch in your kind of equation with the galaxy images in there. Yeah, what exactly are those images?
Yeah, sorry, I should have said that. So what this is so let's go back to this actually. What I've done is show the top activating, sparse feature, right? And so that corresponds, that's sort of the ranked ordered list of, you can imagine a bunch of these galaxy images. And then, their activations actually sort of are like it's basically like how bright the point is on the left plot. Now, so when we come back to this, what I've actually shown is just, as a representation of the feature activation strength, I'm just showing the picture there. But really what it is the activation strength of the feature, right? Yeah, thanks for clarifying that. I should have said that.
Ken, did you?
So one thing that the theoretical people and also galaxy information people are interested is the escape fraction of these ionizing photons and emission line photons. So I was wondering if you can relate to some of those physical parameters, physical value of those parameters through these morphological types or emission diagrams that you're using.
Yeah, absolutely. That is one thing that I'm also very excited about. I think the directly training and trying to obtain those a prediction for that is going to be hard because the sample size is not huge. But what we could do is learn some auxiliary properties like O3 strength, for instance, and just try to find galaxies that look something like this, which I suspect a lot of these are going to have high escape fractions. I mean, and it would also be interesting to sort of get more latent variables and see if you have like sort of a differentiation between, say, green peas and other like sort of more other types of like sort of high escape fraction galaxies. And understand whether the morphologies of them sort of all fall in one family or if they can actually break apart into multiple.
And then another thing you can do is to apply this same methodology to the simulated galaxies.
Yep.
And then the simulators can calculate the escape fraction ab initio way. So you can compare those two answers and see how that plays out.
Yeah, so that would be a fabulous idea, except that model misspecification of deep learning, it tends to really get in our way. And so the difference in domains, right? Really just like the small changes in morphology and small like systematic like differences in noise, like that actually it poses a huge barrier for applying this between, say, observed objects in simulation. So I think we are still sort of in early days in terms of knowing how to address that best, but that's absolutely the goal that we would love to go to.
Great, thanks.
Thank you.
Let's thank John again. Next we have Gabby.
Yeah, we already asked.
Should I start?
Yes, hopefully the light will go down.
Okay. Hi, everyone. My name is Gabriella Contardo, also Gabi. And I'm going to present you some follow-up work we did, follow-up analysis we did on this cosmology with one galaxy project that Paco worked on. So the original title was No Degeneracy is All You Need, but it turned out to be not quite accurate. It's not wrong, but it's just not quite accurate. So, and I couldn't come up with anything better than that. So, no. Should I point it out somewhere specific? Okay. So just to give a little bit of context, so Paco a little while ago worked on this paper that showed that if you can predict omega matter up to 10% precision by using the features of a single galaxies by training a machine learning model on the CAMELS illustrative simulation. And after that paper, there were follow-up work showing similar results using Astrid and Simba and other suites from CAMELS. However, they were also showing that if you train on Astrid and you try to predict on illustrious galaxies, then things don't work so well anymore. And this work got a lot of traction. Like people followed up with like trying to look at galaxies in voids, doing the same thing with multiple galaxies. And I think Amanda in the room presented work on this as well, like trying to analyze this result. And on the other hand, cosmologists mostly were a little bit, like they had concerns about this result or about the larger meaning of this result, mainly regarding the impact of the priors in the simulation, the fact that we don't understand so well the subgrid physics, the galaxy formation, and so on and so forth, and trying to understand if these things were driving the result or if we could learn something, bigger about this observation. And so that's what motivated us to do this kind of like follow-up analysis to try to get a better intuition of the underlying mechanism and what we can learn from this, either from cosmology aspect or simulation aspect. And basically in this talk, I'm going to do very simple things to show very simple aspect of the data. And it's a kind of like data scientist perspective on this. But when I was doing this work with my collaborators, this kind of brought up this question, like bigger question of like, what are our goals when we do this simulation, the way we design them, and when we do all of these suites, specifically because the goal is to probably use machine learning, we should be probably careful with how we do things, and I guess that was relevant given the past couple of days question. But so that's the underlying like looming big question behind that. I guess I don't have to spend too much time on this because you probably all are aware of what's going on here, but I will focus on the two simulations in CAMELS that are illustrious and Astrid. They have two cosmological parameters, four astrophysical parameters. From the simulation, you can extract catalogs of galaxies. The galaxies have 13 features, so I will refer to them as feature: gas mass, stellar mass, velocity, information of the subhalos, metallicity, this kind of thing. And you get simulation on Latin hypercube, so varying all of the parameters at the same time. And you get the 1P simulation, where you vary only one parameter at a time. And the cool thing is, illustrious and Astrid are like, different, obviously, otherwise there would be no point. But they share this kind of like large-scale aspect, like 6 parameters, 13 features, but they have different hydrocode, different implementation of some of the astrophysical parameters, and we're going to be able to play with that in our analysis. So first, we want to look at the impact and the effect of the individual parameters, because the original results said basically that we can predict omega matter from one galaxy, because meaning we can marginalize over everything else, right? But what this means is either the features that we use to predict omega matter remain informative despite the other parameters' effect, and if so, then why? Or the other parameters are not impacted those features at all. And so we need to know in which case we are. We can sort of start guessing based on the result of the original work, because some of the parameters were not predictable from the features, but this could be because we can't marginalize over omega matter. So we want to check basically which is which. So a simple test for this is we use the 1P simulation, and we just check how well we can tell apart galaxies that come from the fiducial from the galaxies from a different simulation when we vary only a single parameters. So we try to like eliminate, confounding factors. So if this plot basically tells you the accuracy when I try to classify the galaxy from the fiducial versus the galaxies from a different simulation, so the color meaning which parameters I'm varying, and the x-axis tells you where am I on the parameter range. So -2 would be the minimal value, and 2 would be the maximum value in the range. So as expected, you can see omega matter moves things a lot, so I can classify really well. We could have guessed that from the original results. ASN1 seems to have a strong impact as well, but the 2 AHN astrophysical parameters seems to have basically no impact on the entire, we can't classify. This means that no features are moving based on those parameters. This plot, however, doesn't tell you which features are moved by these parameters, how they're moved, and stuff like that, but it just gives you an idea of the strengths of the effect on all of this 13-dimensional feature space. And so the first point here is that some parameters, they don't have any effect on the feature space, so marginalizing over those is straightforward. We still have the one that do have an effect, and so we still have to figure out why we can marginalize over over the effective one. So this is mainly to give an intuition about this. So we're going to start with less feature, let's look just at 3 features for our simulation, and we could look at basically the estimated likelihood. So let's say my reference simulation is the green simulation on the middle, so it's going to be the green distribution. For all of the other simulations, I can take the galaxies in this 3D feature space. I can fit a kernel density estimator, because I'm in 3D, so I'm allowed, and it's still fine. And I can then estimate basically the probability of the galaxies from the green distribution within the, let's say, orange distribution, orange simulation. And I can do this for all of the simulations, and this gives me this estimated likelihood, or the mean PDF of all of those. And what you can see here is basically there is, in this 3D feature space, there is a kind of a degeneracy plan or an interplay between omega matter and ASN1, where basically I can sort of can still make the galaxies from the green simulation believable to be coming from a larger value of omega matter if I reduce the ASN1, and vice versa. And you can see this, that basically this means that the green distribution is still covered by the blue and the red distribution. And if I start adding features, or if I start adding the metallicity, basically I start breaking this degeneracy, so I lose this I'm cutting, basically those ones are not likely anymore. And you can see this in those plots is basically the green distribution here is not covered by the red one. So basically what it means is that in total we have 13 features, and so the other parameters, they don't introduce degeneracies or enough variance in all of the feature where omega matter has an impact enough to obfuscate omega matter signal. And on the other hand, we also have technically enough features. I mean, if you think about a very simplified case where we have 5 parameters, a linear model, you get 13 features, you should be able to always predict the 5 parameters in a linear case. So in a sense, we're now at a point where we're okay, in the end, it's not so surprising. But another aspect, another thing I want to say is that yeah, people were also discussing, oh, how, you know, the choice of your priors, the range of ASN1 that you decide is going to impact your result, which is kind of true, because if you imagine in the 3D case at least, if you were cutting on your x-axis, so if you were shrinking your Latin hypercube, you would probably increase your precision in prediction, which is why I have beyond explicit priors on the title. So all of those like simple tests were done only on Illustris, but there are, you know, more choices that are done, and that can impact your results. So the hydrocode, the way you implement your parameters, which parameters you put in your simulation, and because Illustris and Astrid are kind of like on a similar footing, it's a nice avenue to like play this game of comparing. So the first thing you can do is that if you compare like a simulation, the distribution of galaxies when they come from Illustris or when they come from Astrid with the same cosmology setting, same astrophysical setting, you can see that the distributions are very different, which is not surprising. I think you would expect that, right? But this is basically, you can, like this plot is giving you the distance, like a metric of distance between the distribution, and same thing, like now instead of comparing against fiducial, I compare Illustris against Astrid. And what it tells you is that even at fiducial, your fiducial distribution in this 13D feature space look different. Again, I mean, that might be expected, right? But it's still, you need to observe that. And this plot, however, doesn't tell you if the parameters have a different impact, the way they move the distribution. We want to know if they move the distribution in the same way. I think specifically for the cosmological parameters. I guess the astrophysical parameters, you would expect them to not move the same way between Illustris and Astrid. And so basically what we want to try is to quantify and compare how, you know, omega matter is moving the distribution in this 13D feature space, and so on. And so right now we're trying to, well, we're doing this with optimal transport. So we have this thing called the Earth mover distance. So basically the idea is that if I give you a distance matrix between the point of the set A and the point of the set B, this Earth mover distance tell me how to move the point from this set A to match the distribution of the set B, and this displacement is expressed as a function of the point in the set B. So basically here you have an example where I pick galaxies from fiducial simulation, I pick galaxies, so in blue, I pick galaxies from a simulation where omega matter is 0.1 in red, and this Earth mover distance is represented by the black connecting the red and blue dot, where basically this tells me, oh, you should move your blue dot, you know, in the direction of that red dot. But in practice, this Earth mover distance is a matrix that sums to 1, so I can basically use it to compute an average displacement vector, which, I mean, eyeballing it, you know, it would be like this way or something. But I can do it, you know, properly without eyeballing. And we can do this for the 13 features, and basically this plot is telling you, well, you can stare at this plot a little bit. This plot is confirming other things that we've seen before, confirming also things that Amanda has observed in her work. So for instance, on the top left, so you can play this game basically for Illustris and Astrid, and this plot is telling you how to move your feature to go from fiducial to omega matter 0.5 in green, and how to move your feature, how the parameters move your feature when you go from fiducial to ASN1 in red, different values if it's dashed or solid. And what you can see is that, so for some of the features, if the displacement vector is the same shape between those parameters, they will kind of like create degeneracies against each other, because you can, you know, cancel the effect by moving one in the other direction. And then you can also see which features will break the degeneracies, because then they don't have this like symmetric effect. You can see as well that, for instance, as expected, ASN2 is way stronger in Astrid than in Illustris, which I guess was you would have absolutely expect. And you can see that then, I mean, if you look more closely, then you can start looking at how, especially for the cosmological parameter, in which feature space Astrid and Illustris behave differently. And I don't know I think this open kind of like conversation, like I don't know if you want them to behave exactly the same or slightly different. But I'm curious to learn more about that. Okay, so the takeaway is that, so basically those tests are just like simple things to try to understand, at least from a data science perspective, the mechanism behind the original result. And so at the end of the day, omega matter creates strong displacement in this feature space, so the galaxy is observable, enough so that you have little overlap between the distribution when you don't move anything else. And on the other hand, a few other parameters that do have an effect on the features, especially the ones that are informally for omega matter, these effects are not strong enough to obfuscate omega matter signal in this space. So basically, if you really wanted, I think if you really wanted to obfuscate omega matter signal, you'd have to like have other parameters that are stronger in this y-axis, basically. And so this in itself like explained the original results from cosmology with one galaxy. So we perhaps even shouldn't be surprised that we're allowed to able to do that, because is it that surprising that omega matter is a strong like displacer in the data in the galaxy's feature? I don't know. Like this is for you to answer. And on the other hand, so the other priors like the hydrocode and the way you implement your parameters heavily influence the features and their distribution and the way they move. And so that makes hard to transfer between suites, but that also makes it really hard to figure out how you can transfer to the universe, right? Because we don't know in which regime we are. And this circles back to all of this conversation we had yesterday about, you know, how we find the features that are robust and blah, 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 and all of that. And I'll just end with this sentence by Mike Blanton that I think is well phrased, but I don't know what to make of it. And that's basically, this opened a lot of questions for me that if you have strong opinion about all of this, I'm happy to discuss. Thank you.
Any questions? Yes, please.
Okay, hi, thanks for the talk. I think you showed how change in omega matter changes galaxy properties, but do you have an intuition of the process of this? Is this because of mergers, or it changes the number of mergers or something, or have you any theory for that?
I think I'm probably the least qualified person in the room to answer that. But no, but hopefully this plot might at least point to where we should look, so then we can, but it's kind of, the risky part is that it might be a posteriori explanation, which is not ideal. But at least we can come up with explanation. I think it's not insane to think that omega matter will lead to like more massive galaxy, like the masses of galaxy distribution. And the flip side of your question, which is important to answer, is that is it reasonable to think that there is no astrophysical parameter that will create effects that are at least as similar variance or strengths? Because maybe that's perfectly reasonable. Like I don't know, like what do you need to like create this type of displacement? I don't know, but hopefully this is a direction to like look at. But
any other questions? Daniel?
Thanks. So I guess, so you identify for illustrious TNG in the suite with 6 parameter variations, this degeneracy between like supernova 1 and omega matter, and then with enough features, then you can break the degeneracy. So I guess my question is, what about like all the parameters that could also be degenerate and we may not even know about them? I mean, and this is maybe something that can be tested with like, the 28 parameter variations.
Yeah, that would be cool.
There could be any number of other parameters degenerate and anyway.
Yeah. So I think we could play the same game with the 28 parameters. I just have to find a way to make more nicer plot. But we could do the same thing, right? I think it would be cool actually to figure out for different observable where the parameters are impactful or not. For the degeneracy, I think at the end of the day, it's not. I'm not so much. I think creating true degeneracies in enough of the feature space is going to be hard. Like it's almost surprising that you have it with ASN1 and omega matter in 6 parameters. Like what are the odds? It's weird, but I think it's more about creating variance. Like you need parameters that might create variance. I'm still trying to wrap my head around that, but.
Any other questions? I have one quick question. Is one way to think about these optimal transport displacement vectors as almost like a derivative along like omega matter or ASN? So
I think we discussed that yesterday with other people. I would have to sit down, but I think it might be similar, yes. So I think there are probably many different ways of doing this. It's just this one came up.
Yeah.
Yeah. And by the way, this is a like crude linear approximation, obviously. So, and I removed the error bars on that because, of course, if you're trying to go from a Gaussian with STD1 and a Gaussian with STD2, but still the same mean, like you have no displacement as average, but you still need the error bars to like figure out that you change your distribution.
Well, let's thanks. Next we have Julen.
So, hi, I am Julen Expósito, a PhD student from the EAC, and I'm going to talk about the work I have been doing trying to construct a supervised neural network trained with simulations to infer dark matter density profiles. In my case, with a focus on dealing with the core versus cast problem. So to give some context, in the lambda CDM model, the halos have a characteristic mass density profile that have a very pronounced inner slope. But for some observations of dwarf galaxies, they tend to prefer fits like this. So we say that these galaxies have cores and the other galaxies has cusp. You can explain this in the current paradigm by the effects of baryon feedback, but in general, it's a very controversial topic, mainly because with the traditional techniques, doing dynamical modeling to infer dark matter density profiles, you are not able to constrain the inner slope in a way that allows to rule out or assume the presence of a core. So as many people with many things, we try to skip the problems of traditional techniques with machine learning. The idea here was to create a neural network that use positional and spectroscopic information of the stars, so information you can obtain from surveys like Gaia, for example, to infer the value of the inner slope of the density profiles. So first, we need a good sample of simulations to train out network that meet certain criteria, mainly to be zoom out hydrodynamical simulations that give us a lot of cores and a lot of cusp, and to have enough resolution to be able to more or less accurately extrapolate the value of the inner slope near the center of the galaxy. We are using Hao galaxies that give us a lot of galaxies that meet this criteria in a variety of mass ranges. What we have done is to construct a CNN. So we take its galaxy, and we make a lot of projection in the sky plane to have a lot of orientation and expands our data set. And for each projection, we wanted to create maps that have all the relevant information of the stars. So we have the observables, we have the position, the 2D position of the stars, and the line of sight velocities. And we have constructed two maps to define each projection. 2D PDF with the positions of the stars, and a 2D PDF with the relationship between the distance to the center of the galaxy at the velocity of the line of sight. These two maps enter two different convolutional channels that goes parallel to each other and independently, and then they joined in a final sequence of dense layers that end up giving us a one-dimensional PDF with the inference for the inner slope. And we say that the prediction of the neural network is the maximum of that distribution. So we can test, we have tested this with all the dwarf galaxies of Nihao and test it in Nihao also. And the results are pretty good. Mainly 80% of the galaxies have a predicted inner slope that differentiates from the real value with less than 0.1 in the logarithmic scale, and nearly 95% less than 0.2. So these are values that allow us to rule out or assume the presence of a core. So this can say if any Hao galaxies have a core or not. And we also test it with 4 real dwarf spheroidal galaxies and compare it with what we obtain when inferring the density profile with GENS modeling. And the results are very consistent. This was a very preliminary test, but it seems that we are walking the right path. So we further developed this model to be able to infer the complete mass profile. This is work primarily done by Jorge Sarrato that is going to talk after me, explaining all the things he has done, so I'm not going to stop a lot of time here. But the important thing is that now this modified version of the network, doing mostly the same, is inferring, is giving us a joint PDF with the values of the enclosed mass at different radii, so the complete mass profile. What I have been doing these last months is to try to expand the network with more information. So in the local group, we have a lot of galaxies with proper H1 observations from which we can construct gas rotation curves. And as you know, this is a very good tool to infer density profiles. So why not try to apply the same logic with the stars to the gas and make more maps to input our network? What we have done is to pass its projection through Martini to construct synthetic resolves H1 observations. And with those spectral data cubes, we have constructed 3 maps: a H1 flux map, a velocity map, and a velocity dispersion map. These 2 maps are masked to ensure a good signal-to-noise ratio. So there are a lot of galaxies in our sample that basically don't have very good gas information. And we just rule out those galaxies. So now we have this plot. I'm going to stop a while to explain this properly. Here you have the ratio between the predicted mass and the real mass in different radii relative to the Hadar radius. The lines are the mean value for all the test sample at different radii, and the shadow regions are the 1 sigma dispersion. So when you only use star maps, so the 2 channels of the star maps and some global parameters like the Hadar radius and the mean velocity dispersion, you don't have any bias, really, but the dispersion is very bad. In fact, it's worse than what I had when only trying to infer the inner slope. I don't know why. But then when you use the gas information on 3 channels for the gas maps and global information of the gas, the dispersion is lower. And the important thing, when you use everything, so 5 channels that goes and then joins and so, the dispersion is even lower. So in fact, the neural network is capable of more accurately predicting the mass profile when giving gas information along with the star information. So yeah, the conclusion is basically that everything is fine, everything looks cool, but I'm doing this with Nihao galaxies only. So I'm training with Nihao galaxies and testing with Nihao galaxies. So this obviously needs a lot of cross testing with different simulations to see if it is generalizable, or I'm just only constructing a mass estimator for Nihao galaxies, which is nothing. And Jorge is going to talk a lot about this. So thank you.
Any questions?
Yes. Hello. Thank you for the talk. I have a lot of questions, but I want to ask some clarification question on the data set. So for Nihao, what is the resolution of Nihao? Because usually when you look into like hydro simulations, there's a resolution limit of how low you can resolve the core. Like at one point, the simulation can no longer resolve the core. So I guess that's kind of like my first question. And my second question is, what's the distribution in the simulation versus like core versus cuts? Like how many fraction of the galaxies that you train on is core and how many fraction of those are cuts?
Yeah, so the resolution is, it depends. There are different resolutions depending on the galaxies, as we are mixing everything, but more or less 10 to the 5 solar masses to the star particles. And yes, that is something we are worried about, because the softening length is about 300 parsecs. So we are using, when constructing these maps, we are not sure with a lot of galaxies if this is correct or is just noise in a lot of time because of the softening length. But it seems to work fine. And then with the dwarf galaxies, because when the galaxy is outside some mass range, you always have CASP. But in the dwarf galaxies, I think it is like 70% of the dwarf galaxies have cores anyhow, more or less. But I have to check that out.
I have a follow-up, but I'll let you ask your question.
I think we should save it for a coffee break.
Sure.
Yeah. Well, Julen again. Next we have Jorge.
Okay, thank you. So yes, I'm Jorge Sarrato-Alós. I'm from the Institute of Astrophysics of the Canary Islands. I'm also a PhD student. And I'm going to present this work, inferring dark matter profiles in dispersion-supported galaxies with simulation-based inference. And I'm going to try to not repeat a lot, but it's going to be a bit difficult because I'm also collaborating with Julen, and it's a very similar topic. So first, why do we want to use machine learning for this? Well, it's true that there already exist some techniques to obtain the dark matter profiles of dispersion-supported galaxies from the projected stellar data. They have some drawbacks, and especially what impedes to apply it to a lot of galaxies is that it's very computationally expensive. So researchers have looked for different ways to obtain the enclosed dark matter in galaxies, and they have come up with these mass estimators, which are equations that are able to use the half-life radius and the line of sight standard deviation of the velocity of the stars in order to obtain the mass enclosed within a green radius. So here I'm showing 5 examples from the literature of mass estimators that are derived in different ways, and each of them aims to calculate the mass enclosed within a different radius. And so with machine learning, what can we do? We have the advantage that we don't need to rely on strong dynamical assumptions, and also we may be able to adapt to different dark matter profiles depending on how we design our output. And basically, we are just limited by the extent and the quality of our training set. So our training set are cosmological hydrodynamical simulations. We have the Nihao galaxies that Julen already talked about, but I also gathered simulations from the Auriga project and the FIRE project. And here you can see that they span different regions in the 2D plot of half-life radius versus stellar mass. So for all of these galaxies, we make 64 rotations uniformly distributed across the unit sphere. And we create a dataset of Nihao and Auriga galaxies for training. Here you can see the distribution of the projections in this quantity, which is the mass enclosed within the projected half-life radius. So you can see that for Nihao and Auriga, the the distribution is the same one. This because I forced it to be that way by removing additional galaxies. So that way I have a balanced dataset for each mass bin. And that way I will not introduce bias towards Nihao or Auriga galaxies. And you can see also distribution for FIRE. And so for all of these projections, we get inputs, which Julen already explained. It's these 2-dimensional probability distribution functions of projected quantities of stars. And here we have the architecture. Again, it's this 2-branch convolutional neural network that then we concatenate the results, and it goes into some dense layers up to a layer of n neurons, where n is the number of points of the mass profile that we want to predict. And also I want to bring your attention to basically the main change, which is this concatenation of the half-life radius and standard deviation of the velocity of stars along the line of sight. So basically, we train this with a mean square error, where the labels are masses extracted from the simulations. And then we use the output of the penultimate layer in order to train a normalizing flow for neural density estimation. And that way, we obtain this kind of posteriors, where each dimension is the mass enclosed within a different radius. Here I'm cutting the corner plot so that it's not so huge. And hoping to some results. First thing is that the posteriors are very well calibrated, so the real value is enclosed within the confidence level, the right amount of times. And of course, we can transform this posterior to an actual profile. So for that, we get the median of the posterior as the mass enclosed within a given radius, and the 1 sigma region as uncertainties. So here I'm showing the numerical profile from the simulation in blue, and we have different markers that are the mass estimators that I told you about before. And then in pink, we have the results from the CNN. And of course, we have this for all the projections in the sample. And we want to summarize this in one only plot that I'm trying to explain well. So on the y-axis, we have the predicted mass divided by the real mass. And on the x-axis, we have the different radius at which we are predicting the mass. We have the mass estimators as markers, and the 1 sigma dispersion of their predictions as error bars. Then for the CNN, we have lines, which are also the median predicted, and shadow regions that indicate the dispersion of the predictions. So what we can see here already is that the bias is improved from the mass estimators, and also the dispersion. And furthermore, we are also providing mass estimates at different radius where no mass estimator previously existed before. And sorry, I forgot to tell, this is training on Nihao and testing on Nihao. So I'm going to show now what happens when we train and test on Auriga. Basically, everything still works fine. And now we're going to the fun part, so where we're trying to cross-test, and everything fails. So this is what happens when we train on Auriga and we test on Nihao. That's the blue line. You can see it's very different than what happens when we train on Nihao and test on Nihao, which will be in orange. What can we do? Well, we tried training on Nihao plus Auriga at the same time. Is the pink dashed line that recovers the correct behavior. Also, we can do it the other way around. And testing on Auriga when we train on Nihao doesn't work, but we can train on both and recover the good results. However, what will happen is, well, everything is thinking, when you train on these two suites of simulations and test it on a third one. So first we have these plots where we have the good results of the Auriga and Nihao dataset. And we can separate the validation galaxies between Nihao and Auriga, and we recover the original results, which is nice. And now, actually, what happens when we try this model on fire? Well, first I'm showing what happens when we train on Nihao or train on Auriga and test on fire. We have biases. The 1 sigma dispersion of measurements is worse than mass estimators. But now what happens when we train on both and apply to fire? Well, I'm showing 3 different realizations. Basically, what we have is there are different realizations of the training that all are able to apply well to Nihao plus Auriga. However, they give different results for fire, and none of them are better than mass estimators. So our model is not able to generalize, even though we have populated the training space with more galaxies from different suites of simulations. And that will be the conclusions. It works well for the same suite of simulations that it's trained in, but it can't generalize. So for future work, we are hoping to leverage domain adversarial neural networks, and we expect this to help us to train on one suite of simulations and apply to the other. And also, we want to test what happens with graph neural networks, as it seems to be a better way to encode our inputs. So thank you. That was it.
Any questions for Jorge?
Hi, thanks. So when you say you trained on Nihao and Auriga together, is that doing something unsupervised to improve the feature extraction, or are you just concatenating?
No, I just concatenate. The only special thing, let's say, that we did for preparation for that joint training is so cutting the distribution of galaxies so that, yeah, the distribution of masses is the same. We have the same number of Nihao and Auriga galaxies for each mass bin, so we are just trying to avoid biases that way, but it's nothing unsupervised, completely supervised.
Okay, and then these projections you're doing, are you doing any sort of augmentation as well for training data?
No, the only thing we are doing is, okay, yes, these projections, so we have several projections from each galaxies, and we have we experimented with doing samplings or different samplings of the same galaxy, so different random samplings of stars. It didn't change much. And yes, the only other thing also, but it's nothing much, is that this orange layer here is a rotational layer, so it's doing also random rotations of the positional map, so of the map of X and Y. That's all the augmentations we are doing.
Okay. Yeah, I mean, you mentioned it with your future work, but I think something unsupervised with the domain adversarial stuff.
Yeah.
But also with like improved feature extraction with these augmentations or equivariants. I feel like that combination together would probably like significantly improve your job.
Okay.
Yeah, thank you for
yeah.
One very quick question, if anyone has. John, make it quick.
Very quick. So I noticed that the coordinates are sort of normalized by the half-light radius, and I'm just curious. That seems like that might cause a varying, resolution, in terms of physical resolution as a function of because the half-light radius changes. Can you speak to why you made that choice?
Yeah. Well, that choice is made because we have galaxies from very different sizes, right? So if we do a fixed size, we have the problem that some galaxies are very represented only by a few pixels. So it's not very good for for getting the information from there. So what we decided to do is to normalize by the half-life radius and then input the half-life radius here, so the network knows the limits of the maps. And that's basically why we did it.
Let's thank Jorge again.